Okay, welcome back to another video lecture for Math 1316, Plane Trigonometry. And in this video lecture, we're going to be covering section 2.4, which is applications of right triangle trigonometry. So to begin with, we first like to have some kind of method for solving any right triangle. And it turns out that we can do this simply from our definitions for what sine, cosine, and tangent are. Now notice here that I have drawn a triangle and labeled it A, B, C. And typically on right triangle questions, we are given either 2 or 3 pieces of information about that triangle. And included in the problem is a statement that the triangle must be a right triangle. If the problem statement does not say that we have a right triangle, then we're not allowed to assume that we have a right triangle. And we could either have an obtuse or an acute triangle, just sort of depending on the case for which angle is given and how big that angle is. Typically, when we are given an acute triangle, it's a little easier, but if we are given a measurement which happens to be obtuse, then there are kind of two different cases that could happen. Technically, three if they give you measurements that cannot possibly form a triangle because they do not satisfy the triangle inequality, which we will talk about a little bit later. Then, of course, we can write that there's no solution to the problem. Now, in right triangles, almost all of the measurements that we're given will work because of the statement that we have a right triangle. As long as they don't give us an angle measurement, which clearly violates the sum of interior angles theorem. For example, had this been 100, then this right triangle could not possibly exist because 100 plus 90 degrees is greater than 180, which is greater than the sum of the interior angles of a triangle. So most of these are solvable and they are unambiguous in that they have one solution. Now, all right triangles can be solved with an application of trigonometry, an application of Pythagoras, and the angle addition postulate, the sum of internal angles of a triangle. So there are three things, and they don't necessarily happen in any particular order. A lot of times when we have a case like this, we do the sum of the interior angles first, then we do a trig ratio, and then we use Pythagoras to find the final side. Okay. So keep in mind that we have the definitions of all 6 trig ratios, and we can use them in whatever sort of fashion we'd like to use them in. But typically, we like to stick to sines, cosines, and tangents whenever possible. So we try not to use secant, cosecant, and cotangent if we can avoid them. And that just goes for ease of calculation with typing things into a technology piece, especially when we have really weird angles like this, which is 28 degrees, 40 minutes. So what we'd like to do first is determine what the third angle in this triangle is. Now we have angle B given as 28 degrees, 40 minutes. And we have side A given as 25.3, and then it'll have a unit on it like inches, centimeters, or meters. But typically in our homeworks, this is included in the answer blank, so we don't have to worry about the unit just as much as we would in, say, a science course. The other thing we do have to be worried about here is whatever rules for significant digits we want to use. But right now, we're just focusing on solving this triangle, so I'll be ignoring significant digits in this problem. Okay. So the first thing that I like to do to solve a triangle is make what I like to call the answer chart. So the answer chart is just capital A, B, and C on the left-hand side and lowercase a, B, and C on the right-hand side so that all of the capital letters represent the angles in the triangle and all of the lowercase letters represent the sides in the triangle. Now notice here that we already have 2 of the angles in a triangle, and so finding the third one is actually relatively easy. We just add these 2 angles together and take them away from 180. But there's a shortcut to this as well. Because we have a statement that this is a right triangle, C will be 90, which means when we add it to something else and take it away from 180, this is the same thing as just taking the complement of B and setting that equal to A. So the complement of B is just 90 minus 28 degrees and 40 minutes, which will give us 61 degrees and 20 minutes. 61 degrees, 20 minutes, or in other words, 61 and a third degree. So once we have the measure of angle A, we can set up some trig ratios. And remember that the specific labeling scheme that we're using on our right triangles likes the angle A as our reference point because it is an angle in standard position. So we like to try to do whatever trig ratios we're going to do in terms of angle A. So if that is possible, we will use A in order to write our equations. So notice here that we have lowercase a, and then we could either find lowercase c, which is the hypotenuse side, or lowercase b, which I've labeled with this x variable right here. It is my suggestion that we always try to find the legs of the triangle and not the hypotenuse side if possible, because then we only have to perform Pythagoras in the forward direction, which means there's no possibility for mistake. It's my experience with students that they sometimes mess up Pythagoras, and this is something that we should try to fix, but we'd like to reduce the possibility for error whenever we can. So we can notice that the tangent ratio is defined as A over B. So the tangent ratio for 61 degrees 20 minutes will be defined as A, 25.3 over B, and we've called our B value X for the purposes of this problem. Now there's some quick algebra that we can do here that will cause X to be our subject, and then that will make the right-hand side 25.3 divided by the tangent of 61 degrees and 20 minutes that will give us the X value in this problem. Now it's important to note here that whenever we're about to do one of these calculations involving a trig ratio, we want to see what kind of angle measurement we were given because there are two different versions that the calculator is prepared to do. At this point, we are dealing exclusively with degree measurements, and so we want to make sure that our calculator is in the degree mode, and this was mentioned in a previous video lecture, so just from here forward, make sure that we're in degree mode when we're about to plug something into the calculator. So next we can take 25.3, but divide it by the tangent of 61 degrees and 20 minutes, and it will give us that our side x is 13.83, or in other words, b is 13.8 when we round. Now notice that this is an arbitrary rounding. I'm not worrying about things like significant digits here. So in your problems, what you would like to do is make sure that you do not round any of the values until the very, very end. In other words, you would write the full 13.83 blah, 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 blah out beside it to perform calculations with that really weird number. And then we'll round it before we plug that in on our homework module. But this particular problem is set up to work this way, so I'm going to go ahead and round it here. So now we have a right triangle where we know lengths A and lengths B. So to find length C, we simply need to apply Pythagoras to this. In other words, A squared plus B squared equals C squared, or C is equal to the square root of A squared plus B squared. So we can perform Pythagoras in the forward direction, 25.3 squared plus 13.8 squared, and then take the square root of that result, and that will give us that our hypotenuse side is 28.8 units long. And once we have our, what I like to call the answer chart filled out, we have in fact solved the triangle. All we have to do is determine which particular pieces of information were asked for, and this is kind of an application of common sense. Had this been like a building that was 25.3 high, and then we have an angle of elevation from a point away from the building in the horizontal direction equal to 28 degrees 40 minutes or 28.6 degrees, then we could say how far away from the building am I standing, and that would be this b value right here. So there's some common sense that we have to kind of look at when we get our answer chart filled out, but the point of this was to fill out our answer chart, and then that from there we can determine which pieces of information are being asked for. This particular problem just said solve it, and so all 6 of these values is the solved triangle. So I've cleaned up the board and put a second example up. Here we are asked to solve a triangle given 2 sides as opposed to 1 angle and 1 side. Now notice here that we have no idea in what way to figure out what capital A and capital B are from the beginning. What we want to remember is that any right triangle can be solved with an application of Pythagoras, an application of a trig ratio, and then lastly, one of the sum of the internal angle of a triangle postulates. So we can do these in any order, and this is meant to show you that the order is not necessarily the same thing every time. You just kind of have to use your common sense. So we're going to ask, what's the easiest thing that we can do? Well, we have a right triangle where we know the 2 legs already, so we can go ahead and apply Pythagoras' theorem where we know 2 sides, a squared plus b squared is equal to c squared, to figure out what the hypotenuse side length is. So that will give us 44.25 squared plus 55.87 squared, and that's going to give us a measurement for side C, 71.27. And remember, you don't want to round these values. If at all possible, you'd like to perform the calculation with the full value just before you plug it into Pearson, because they're very, very strict about the rounding here. Okay, so to find A and B, we have a couple of options here. But if you recall, we like to use capital A as our reference point on these triangles. So every trig ratio we set up, we would like for it to be in terms of A. So in other words, we'd like to find capital A and then use the sum of the internal angles theorem to find capital B. Now, in this case, we have a situation where the tangent of A, which we do not know, is equal to A over B, 44.25 divided by 55.87. Now, the way that we can get the capital A by itself, the way we can isolate that and make it the subject, is by applying the inverse tangent command on the calculator, or in other words, the arc tangent command on the calculator. So the way that we do this, if we already have the trig ratio, but we don't know the angle, we can take the arc tangent, which in the calculator is tangent to the negative first power. But for the purposes of these video lectures, and this is just a personal preference for me because of the textbooks that I learned out of, I like to write out arc tangent, which can be abbreviated this way, arc tan. So arc tangent is just the second key and the tangent command in the calculator. So when we type this thing out, we'll have the arc tangent of 44.25 over 55.87. And in the calculator, I'm going to try to get it where you can see it. It looks like this, tangent -1 of the ratio that we had. So if we run this, it's going to give us an angle measurement for A, which is 38.38. Now notice that we could be asked to put this into degrees, minutes, and seconds. And if we were to do that, then this thing would be 38 degrees and 23 minutes. So there's just 2 different versions of the same answer, but I'm going to leave it as a decimal for the purposes of this. Now remember that we can find the angle B by adding together A and C and taking it from 180, or recognizing that this is a right triangle, we can simply take the complement of A and set that equal to B. So that's going to give us 51 0.62 degrees. Once we have our answer chart filled out, then we have solved the triangle. Remember, it's an exercise in common sense. If we had some sort of application here, like a building or an angle of declination, that we would have to figure out what these values represent and answer appropriately, because it may not ask us for all 6 measurements, although to begin with, your homeworks do start by asking you for all 6 measurements. So I've cleaned up the board and put an example of what I meant by an application on the board. So this is a question that says to find the declination angle for a building 97 feet tall to the street that is 42 feet away from it. So notice we can draw this vertical line representing the building that is 97 feet tall. Then we can draw this horizontal line representing the lateral distance from the building to the street, which is 42 feet away. Now we do not know C, so if I label this thing, I'll have capital A is this angle here. I'll have capital B is this angle here. And then I'll have capital C is the right angle at the base of the building. Now notice here that we want a specific angle. So I'm going to make my answer chart, because it's my preference every time we have solve a right triangle question in any form, that we try to get all 6 measurements and then use our common sense to figure out what was asked for. Is this necessarily the most efficient way? No, but it does in fact work every time. And so if you get in the habit of doing this, then you're doing a little bit of extra work, but you know you have the correct answer somewhere in this answer chart. Okay, so what do we know? Well, we know that capital C is 90 degrees because this is presumably a building which is flush with the ground. We know, based on our labeling scheme, that 97 is little a, and that makes little b 42. Now, we don't know C, but that is actually okay. Because remember, any right triangle can be solved with an application of Pythagoras, the application of a trig ratio, and then the sum of the internal angles theorem. So we have 2 sides already, which means we can go ahead and do our Pythagoras theorem with 97 squared plus 42 squared, and then take a square root. That will give us that C is 105.7. Next, we can find capital A, because remember, we like working with capital A because it is the angle that is in standard position here. So we can write that the tangent of capital A was 97 over 42. And then again, by applying the arc tangent to this problem, we can isolate A, typing in arc tangent of 97 over 42. That's second tangent 97 over 42. And it gives us a degree measurement for A, which is 66.59 degrees. Next, we can take the complement, recognizing that this is a right triangle, to find B. That gives us 23.41 degrees. And now we can actually look at the problem and decide what it is that they were asking for. Now notice this says an angle of declination. So an angle of declination means that we might have some little guy standing up here on top of the building. And from his line of sight, we want to know what angle this forms looking down at the street. We'll notice here that if this guy is sitting up on top of the building looking straight out, then his line of sight is actually parallel with the lateral distance from the base of the building to the street, 42 feet away, which means that this hypotenuse side is a transversal line, and we can apply theorems from Unit 1 in order to find the angle of declination. Now notice that the angle A is 66.59 right here, and that because of the alternate interior angle theorem, this angle here must be consistent with the angle of declination there. So when it says find the angle of declination, what they are actually asking us for is A. And so we would report that the angle of declination is 66.59 degrees, or we could put it into degrees, minutes, and seconds if we were asked to do so. So some key takeaways from this section. Remember that any right triangle, we like to work with capital A whenever possible because that is the angle in standard position. And then furthermore, we like to find all 6 pieces of information about the triangle just so that we have all of the possible information we could be asked for, especially on some of these step-by-step problems where it gives you find this thing and then you hit enter and it says, okay, great job. And then it gives you another question in the same context. It's okay, find this other thing. Then you have it all right there in front of you. Lastly, remember that any right triangle can be solved with an application of Pythagoras, the sum of the internal angles of a triangle theorem, and a trig ratio, not necessarily in any order. And if you can do that, you've got section 2.4.